So my name is Maaike Vollebergh and my thesis is called Incorporating Flexible Track Use in the SAT Model of the Dutch Railway Timetabling Problem. That's a lot, but I will break it down into pieces with you. I did this thesis, of course, in cooperation with the Netherlands Railways. So what is our goal? Our goal is to generate a timetable, in our case for NS. So this is what a timetable looks like. I guess it looks familiar to most of you. So what we see here are a few aspects. So first, in the first column, we see the departure time of the trains. Second, we see the routes of the trains and where they stop. Third, we see the tracks or the platforms at which each train leaves. And lastly, we see the type of each train. So a characteristic of the Dutch timetable is that it's cyclic. So we have the same timetable every hour. So we create a timetable for an hour in such a way that we can repeat it hour after hour along the day. To generate this timetable, we use the following input. It's what we call the line planning. And that consists of the routes of the trains, as you can see, and the types of the trains. So we don't know departure times yet, and we don't know the tracks. And we do know the routes of the trains and how many times an hour each train is supposed to drive. This is also what is currently used as input by human planners to create a timetable, as well as some conflict signaling methods, systems. But what we'd like to do is to create a mathematical model to improve this process of generating a timetable. So there is a current approach that is mostly used and has also been used by the Netherlands Railways to find a timetable. It looks like this. So we still have the line planning as input, but we have another thing, and that's the tracks. So we have to know beforehand for each train the exact route that it will take. And then we can solve this problem. But this problem doesn't work completely anymore, and I'll tell you why, or why this could be a problem. So I have a small example here. We have two trains, a yellow train, a blue train. And the yellow train comes from The Hague, goes to Leiden, and then continues its way to Haarlem. The blue train is coming from Schiphol, going to Leiden, and then to The Hague. What we see is that these trains have to cross at any point in Leiden, either from the bottom track to the top track or the other way around. And what we see here are the default routes that we would use for a train, namely to drive on the right for as long as possible, just as you would do with a car. So if we have this starting point for creating a timetable, so the yellow train is at the bottom track in Leiden, and the blue train is coming from Schiphol, then we see that we have a problem, because these trains will be at the crossing in Leiden at exactly the same time. So it's not possible to create a timetable. But if you are a bit more flexible, then you see that there's another option for routes for these trains. So this yellow train goes to the upper track in Leiden already before the station, and the blue train continues its way on the bottom track just until after it passes Leiden. The crossing of these two trains has then changed. So if we have the same starting solution or starting point as before, with the yellow train now only at the upper track in Leiden, then we see that these trains can just continue their way, and we found a solution. So this is, in very small, what we'd like to do. So a human planner we can see, just change these routes, and there will be a solution. But you can imagine that for the whole country of the Netherlands, it's not that easy to know beforehand which route you have to take. So that's what my approach consists of. So what we'd like to do is take this line planning again as input and decide on the departure times as well as the tracks at the same time. And in this way, we hope to be able to find a timetable. So now in a bit more detail, to model this idea, I introduced the open-ended periodic event scheduling problem, also OPESP. Well, you can forget the name, but it has 4 main ingredients. So it has a period, t, in our case 60, because we're creating a timetable for 60 minutes. Second, a set of periodic events. Third, for each event, the number of options. And fourth, a set of constraints. Well, what does this mean? Let me give you a small example. So we have 2 stations here. We have station 1 and station 2, where station 2 has 2 platforms, A and B. We see that if we want to schedule a train going from station 1 to station 2, we see that there are here 2 options. So we have the event, namely the departure from station 1, which you can see here in the dashed circle. And we have 2 options for this event here in the smaller circles, namely taking route alpha or taking route beta. Then we'd like to create a timetable. So we have to give the times to these departures. In the previous approach, this was done in the following way, namely give each event a value between 0 and 59, the minute at which this train departs. In my approach, we extend this domain. So each event I is assigned a value between 0 and hi times 60 minus 1. And then a value in the kth interval of 60 corresponds to choosing the kth route option. Well, to visualize this ID, so we here have this whole line of numbers. You see that, for example, here, I is assigned a value between 60 and 119. This means that route 2 is chosen, and the departure time here will be around 30. This way we extend the domain, and we decide on the route and the time at the same, with the same variable. And this may seem unlogic to use this way, but the reason behind it is the SAT formulation that I'm using to solve the timetabling problem. We're at the math event, so I'm throwing in a bit of formulas, just a bit. So in the SAT formulation, we use propositional formulas, which contain of propositional variables pi, which are either true or false. And we use connectives to create like a sentence or a formula with them. And then this SAT or satisfiability problem consists of the question, can we find values for these variables pi such that the formula is true? Now, how do we encode timetabling problems as SAT? We use propositional variables p, x, k for every original variable x, which is the departure, and every k in their domain. With the following meaning, p, x, k is true if and only if the departure time will be smaller or equal to k. For more details about this, I'll refer to my thesis. This is just to give you a small insight in why I use this approach. But for now, some experimental results. For the experiments, I used this part of the Dutch railway network. You probably cannot read it, but there's Den Helder in the north, and we're going all the way to Amsterdam. And yeah, so that's the network that I used. In the previous approach, where we used this default routes, but driving on the right for as long as possible, no solution can be found. But if we use my approach, with using different route options, a solution is found in less than 40 seconds. So, to conclude, in my thesis I introduced the open-ended periodic event scheduling problem. I incorporated this method in the SAT model, and I solved it for a substantial part of the Dutch railway network. Well, all of this was really useful for the Netherlands Railways. Already some follow-up research has been done by another student, Renate van der Knaap. She used an iterative approach with a feedback mechanism to improve the method. And the method is seen as very promising, so more research will be done in the near future. And then hopefully in, let's say, 10 years, we'll all be using the timetable created by incorporating flexible track queues in the SAT model of the Dutch railway timetabling problem. Thank you.